Hello again. In this video, we are continuing our discussion of convolutions, and we have just seen in the notes how convolution is useful with the convolution theorem. It says that if we want to, the main implication is that if we want to find the inverse Laplace transform of a product of functions, then we can convolute those functions. And remember, the order of convolution does not matter, so we can do f star g or g star f. So we are going to apply this in exercise 1. We want to use the convolution to complete the introductory example, which we saw in the previous video, but we're specifically going to have that g of t is equal to t. So that is, we're going to solve this initial value problem, y double prime plus y equals t, where y of 0 is 0 and y prime of 0 is 0. Well, we're going to use some information that we have in the introduction of this lecture that we saw in the previous video. We can look at the right-hand side. The Laplace transform of t is 1 over s squared. So the work at the introduction then will imply that y of s is 1 over s squared times 1 over s squared plus 1. And just tracking back up real quick to see that, we have that y of s is 1 over s squared plus 1 times the Laplace transform of g. So we're just multiplying by a 1 over s squared. So then, continuing from there, we're going to write this as a capital F of s and a capital G of s because we need to do that to use our convolution theorem. And we are going to say that f of s is 1 over s squared and g of s is 1 over s squared plus 1. Now remember, the order of this doesn't matter, so we could switch it, but the basic definition of a convolution says we take t minus v and plug it into f and v and plug it into g. So I am, in this solution here, I am choosing the easier function for f, and I'm choosing the slightly more complicated function for g. Now notice, we know what the inverse Laplace transform of this function is. It's t, because, well, we just got there. And we know the inverse Laplace transform of 1 over s squared plus 1 squared is the sine of t. So that means, then that the inverse Laplace transform of, sorry, that's a typo, that's a capital Y of s, is the inverse Laplace transform of both of those things. That comes from our convolution theorem there. And that's equal to f star of g. Well, f we know is t, and g we know is the sine of t. So we're going to convolute t and the sine of t. And notice that t is the simpler function, so that's a nicer one to substitute in, t minus v. But again, we could reverse the order if we wanted to, and it doesn't matter. So plugging into our formula for convolution, the integral from 0 to t of t minus v times the sine of v dv. Best way to integrate this is going to be to distribute the t and the v, although you don't absolutely have to do that. You can use integration by parts right from here, but it might be a little bit easier to distribute. So that's what I've chosen to do here in this solution. Distribute the sine of v to both of those. Now remember, t is a constant because we're integrating with respect to v. So integrating this is easy to do because t is a constant. Sine integrates to a negative cosine. This term, however, is a product, so it will require integration by parts. And for this video, I'm not going to show the details of that, but you can work through that on your own. You do get both of these terms by applying integration by parts there. So we have negative t times the cosine of v, that comes from here, and minus sine of v plus v cosine of v, that comes from there. And that needs to be evaluated at 0 and t. We will plug that in. A lot of the 0 terms will go to 0. And we are left with simply t minus the sine of t. So what that means for the solution here, oops, I don't know where my text went. I'll just type it up then. So what that means then is that y of t, our solution to the differential equation, is equal to what we found here, which is t minus the sine of t. So that right there is our solution to our initial value problem that we wanted to solve in exercise 1. And we obtained it by applying Laplace transforms and convolution.